Take a look at an example of a two-proportion hypothesis test. And I'm going to go through the 4 steps that we normally go through, and then I'm going to translate that into MyOpenMath here. So it says tests claim that the proportion of men who own cats is smaller than the proportion of women who own cats at the 0.005. Ooh, that's tiny significance level. Okay, I'm dealing with proportions, so I'm using P. So my null hypothesis, whenever I'm comparing two portions, it's going to be the same. It's going to be first group, and let's say proportion for males is equal to the proportion for females. Alternative hypothesis, the proportion of males is less than the proportion of females. So the claim here is that men who own cats, that proportion is smaller than the proportion of women who own cats. So they're using M for male and F for women. So a little bit of weird notation going on, but that's what they have going on here in MyOpenMath. And I just want to show you another way to write these hypotheses. You could have also written this as moving this PF to the other side. The null hypothesis is that the difference in male minus female is equal to 0. In other words, there is no difference. So the null hypothesis assumes the groups are the same. That's really where this 0 in the null hypothesis comes from. No difference in the groups, a difference of 0. So you could write it either way there. Likewise, for the alternative hypothesis, male minus female is less than 0. So either one of these ways to write the hypotheses is fine. Now, if I have it set up like this, this looks like it's going to be a left-tailed test. I'm going to shade in the direction of that arrow. So I'm going to be using that table value when the time comes. Second step. I'm going to do a little bit of scratch work before I get too far into that second step. So I want to make sure that I understand both the groups. So for male, I have a sample of 60 men, okay? So my sample size for men is 60. And it gives me a success rate for this sample of 35%. Okay? That tells me the failure rate for men is 65% that don't have a cat. 35% of this male sample have a cat, 65% don't. Now, when I'm working with a hypothesis for two proportions, if I'm assuming the two groups look the same, I'm going to need to pool together all of my successes and failures. In order to do that, I need to know how many men in this sample owned a cat. So to figure out the number of men that owned a cat, my X value here, I can look at 35% of the 60. So I can do of the 60, 35%. I can multiply together number of terms times the probabilities, and it'll give me the number of successes. If I type this into a calculator, 60 times 0.35, I see that 21 individuals in the sample owned a cat. I'm going to do the same thing now for female. The number of females in this sample was 20. That's really small. So technically, I'm probably not going to meet the assumptions here because that is so small for the number of samples for the female group. It gives me the success rate for female. 55% own a cat. And if 55% own a cat, that tells me the failure rate is 45%. They're complements. To figure out the number of females in the sample that owned a cat, I'm going to take the total number of values times their success rate. So I have 20 individuals times 55% of the 20 own a cat. And I'll type that into a calculator. I've got 20 and 55 gives me 11. So 11 successes, 9 failures. Technically, my assumptions are not going to be met here. I need to have at least 10 successes and at least 10 failures for each of my groups. I'm still going to keep going with the math here. And I'm going to write down a reminder note here. And this is the only situation we've seen so far that we need to do this. But when you have a null hypothesis that says the first group is equal to the second group, and this is always going to be the case when you're comparing a two proportion z-test, when you're looking at two proportions and you're using z-scores, you must pool. Again, anytime you're doing a hypothesis test for two proportions, you have to pool because the null hypothesis assumes the groups are the same. Now, what that's going to do is it's going to average out my success rate. So it's going to average out the 35 and the 55 to ideally get something closer to the middle. To figure out that success rate, your pooled success rate, you can take the number of successes for the first group, add the number of successes for the second group, and that'll give you the total number of successes. And you can divide this by number of samples in the first group and number of samples in the second group. So this is why I wanted to have this number here of 21 males that owned a cat and 11 females that owned a cat, because it allows me to find this pooled value easier. I'm going to combine these numbers together, 21 and 11. So in total for this sample, 32 people owned a cat. And this is out of 60 and 20. If I put this together, 60 and 20, there were 80 people in total. So 32 people had a cat, and that was out of both groups together, out of 80, putting both of the groups together. This gives me a pooled success rate of 32 out of 80, or 40%. And if you look at the numbers, 40% is between the 35 and the 55. This 40% is closer to this 35 because it has more samples there. So it has more weight. It's getting pulled closer to the 35. This tells me that my pooled failure rate is going to be 1 minus that, or 60%. So I have my hypotheses. I did a decent amount of scratch work here to pool. And again, pooling only shows up for this two proportion hypothesis test. And I'm going to use this for my model. My model when I'm comparing groups is going to be first group minus second group is normally distributed with a center of 0. It's always going to have a center of 0. This represents no difference. Next part here is going to be a really big square root. It's going to be my pooled success rate, my pooled failure rate over the number of samples for the first group. I'll have my pooled success rate, my pooled failure rate, and the number of samples for the second group. I'm assuming that these pooled success rates are the same. So I'm going to be using the same numbers for P, and then I'm going to be using the same number for Q for both of those fractions. So I have the square root of 0.4, 0.6, and this is out of 21. That's one of the sample sizes. Oops, sorry, 60. Sample size of 60. I'm being super careful. My other sample size is going to be 20. But I'm still using the pooled success rate of 40% and the pooled failure rate of 60%. 20 samples in the second group, though. I'm going to type that into a calculator and see what I get. And it is a longer square root. That's okay. Out of 20. And when I do this, I get a pretty large standard deviation. I get a standard deviation of 0.1265 or so. So I have my hypotheses, I have my model. I'm going to move on to the third step, which is calculating the p-value. And let's take a look at that in detail. The p-value is going to be the likelihood of my sample data. And this is telling me the order I'm going to be doing my sample data. It says take the rate for male, subtract the rate for female. Going back to my hypotheses, my alternative hypothesis is a less than symbol. So I'm matching that symbol here, less than. My success rate for males was 35%. My success rate for females was 55%. When I type that into a calculator, I get negative 0.20. Labeling things, this 0 here is my center. This 0.1265 is my standard deviation. And this negative 0.20, that's my sample data. So if I draw a picture, in the middle of the curve, I'm going to have 0. And I'm going to shade this from my sample difference of negative 0.20 or less. I'm looking at less than. In order to find that value, I need to calculate my z-score. And I find my z-score by taking the value that I care about, the data. And that data here is negative 0.20. From the data, I need to subtract the center. I then need to divide this by the standard deviation. I have data minus center over standard deviation. I'm going to type that into a calculator. I have negative 0.20 minus 0 divided by 0.1265. When I do this, I get a z-score of negative 1.58. I'm going to look this thing up in my table. It's shaded to the left, so the table value will be my p-value. And I'm going where the negative 1.5 meets the 8. And that happens right here at a table value, which ends up being my p-value because this thing is shaded to the left, of 0.0571. Let's look back at this MyOpenMath question, and let's start filling some things in. First part of this, and we're going to come back to those numbers. We are looking at proportions, so I'm ignoring everything with mu. I'm working with proportions. Null hypothesis is going to have an equals, and I am checking if the male rate is lower than the female rate. So I'm choosing male lower than female. My picture, this thing is shaded to the left. That's the symbol from my alternative hypothesis. So this is going to be a left-tailed test. The test statistic, that's my z-score. I have a z-score of negative 1.58. My p-value, that's this table value. That's that 0.0571. And it says round to 2 decimals, so 0.06 if I round. Compared to 0.005, well, compared to 0.005 here, my p-value is bigger than 0.005. And if your p-value is bigger, this means you will fail to reject the null hypothesis. If you fail to reject the null hypothesis, this means you do not have evidence that the success rate for male is statistically lower than the success rate for female. Now, one of the reasons why I don't have evidence here is because I only had 20 samples for that female group. So I'm not doing great stats in the first place. If I had larger samples, this difference of 35 and 55 might actually be statistically significant. But it's hard to see that with such small numbers. Reminder when you're going through these problems, if you see question help with videos at the bottom, those are video hints for how to do these problems. Let's check our answers. And looks like I've got green check marks all the way through this. That's pretty good. But let me show you how to check this in GeoGebra as well. So I am in geogebra.org, and I pulled up the option for classic. And I'm going to go into probability. If I wanted to look up the z-score and make sure that I'm getting the same table value, I could choose the option to shade this thing to the left. And then inside the parentheses, I can type in my z-score, negative 1.58. This gives me the same p-value of 0.0571. Looking great. If I wanted to check even more than this, though, I can go into statistics. And here I will find all of my hypothesis test called test and all of my intervals called estimates. I'm using z-scores in this problem. I'm looking at the difference of proportions. So I have a z-test of a proportion, that'd be for one proportion. Z-test difference of proportions, that's for two proportions. Null hypothesis is that they are equal to 0. And that was the other way that I had of writing that hypothesis. And it's always going to be 0 for that null hypothesis. It assumes the groups look the same. Alternative, I'm testing if it's less than 0, so I have less than symbol. Number of successes. I'm glad I calculated this. So for males, the number of successes, 21 people had cats out of a sample size of 60. For the female group, 11 had cats out of a sample size of 20. When I do this, it gives me my standard deviation value, 0.1265. So my standard deviations match up. Great. It gives me a z-score of negative 1.58, also really good. And most importantly, it gives me a p-value, if I round, of 0.057. So my results are matching here for both the by hand method and double checking my work inside of GeoGebra. If you're asked to show your work, this is what it looks like to show your work. If you're just trying to get that number really quickly, GeoGebra is a fast way to get that number. I hope that helps. This was a MyOpenMath example for two proportions.